Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today I am pleased to have Khalid here to give us a presentation. He has this technique which I'm interested to learn more about. He has a long history, whereas most people in speech are either engineers or computer scientists. We're going to be addressed today by a mathematician. Who has been at the Paris University, and spent some time in Montreal, spent some time at MIT as a postdoc, and is currently in INRIA. And it's all you.
Thank you, Yasha. So thanks again for welcoming me here and giving me this opportunity to share this fundamental research with you practical guys. And as I said, Yasha, not yesterday, but when we have about that I need some honest feedback about what you really think about what I'm going to talk about, because, of course, the purpose is to go further in more interesting stuff. So what I'm going to present today is a part of the PhD work of Vaid Hanaga, who is going to defend in a few weeks, and with the contribution of Oriol Pont, who is a temporary researcher in our group, and Hussein Yahya, my colleague with whom we co-founded the GeoStat team. So GeoStat team okay, there are, that's the first line.
However, I have been assimilated.
Yeah. So okay, what I said is written there in lines. So and the GeoStat team of Bordeaux is working on nonlinear analysis of complex systems and signals using principles and methods coming from statistical physics, and we have typical applications on geophysics and astrophysics imaging, and also some analysis of heartbeat data. And what I'm going to talk today about is actually these new methods that have been developed in this field of remote sensing application. I found at some point that it is worth to give them a try for speech signals. So the outline of my talk will be the following. I'm going to motivate why are we doing this work, and typically it's because of the nonlinearity aspect of speech, and that we want to look at speech as the realization of complex system. Then I will introduce the formalism that we work with, which is called the Microcanonical Multiscale Formalism, or MMF, to summarize, and describe the basic principles behind this formalism, and see how we can apply it to speech signals. And then I will show what we have achieved so far in terms of applications. So it will be on phonetic segmentation, GCI detections, on sparse prediction, and multiples excitation. And then I will draw some conclusions, and I hope that the perspective will get a lot of exchange. So I don't need to underline that you all know that classical speech processing techniques live in linear world, doing bunch of assumption inherently, and basic here are three of them: that the uncoupling between the vocal and tract and speech source, the laminarity of the airflow through the vocal tract, and the periodicity of vibration of vocal folds. But it is established theoretically and experimentally that there are several nonlinear effects in the speech production mechanism. And typically that there is some turbulent source signal during the production of voiced fricatives. So with this, the laminar flow assumption fails, and that there is nonlinear feedback during voicing, and thus the glottal pulses are not exactly periodic and they are skewed in shape. For plosives, the excitation is time spread and have a turbulent component, and that there is coupling between the glottal airflow and the vocal tract system when the glot is open. So the source and the filter does not function independently. And these nonlinear phenomena, turbulent phenomena, are emphasized in the case of voice disorder, where you have strong complex nonlinear aperiodicity and turbulent non-Gaussian randomness. So if saying this, we would like to look at speech from a nonlinear signal processing perspective, and mainly the people that have been interested in nonlinear speech processing, they were looking at speech in the framework of nonlinear dynamical systems, and typically the dynamical systems that share characteristic with turbulence are called chaotic, and there have been a bunch of tools developed in this area, which is called chaotic signal processing. So I'll give you a brief recall about this. So in chaotic signal processing, the speech signal is assumed, or the speech production mechanism is supposed to be a dynamical system, which is governed by the equation there, that where y is multidimensional, but multidimensional system, but which is unknown, and that the measurement we do, that we capture about speech, are just 1D projection of this unknown, highly dimensional system. And then in 91, there was this existence theorem called the embedding theorem, which says that if you take your speech signal and you take time delays of the signal and you consider this d-dimensional space now, that this the multidimensional signal x shares common properties with the unknown dynamics in y of n. And these common features are typically correlation dimension, fractal dimensions.
What was S again?
S is the speech signal. Sorry, I didn't put it.
Okay.
Yeah. S is the 1D speech signal.
So unknown, high dimensional.
So where? Oh, okay. So S. I see.
So like we could think of Y as the articulators,
Right.
and S as the time series, and then this X somehow is related to the original system.
Yeah, there are some common features, and probably the best known of them is the Lyapunov exponent, which is a characteristic of a dynamical system that remain intact under the embedding procedure, and this exponent characterizes the degree of chaos of the system. So if you compute your Lyapunov exponent and find that it is greater than 0, then you can say that your system is chaotic, and you characterize its degree of chaosity by the value of this positive exponent. When it is negative, it means that the system is not chaotic. Okay.
How good is the assumptive language, the embedding assumption?
Yeah, so I was going to say this here in the drawbacks, is that actually this theorem doesn't tell you how to choose. It's an existence theorem. It doesn't tell you how to choose the time delay t and the dimension d. Okay, and these are very important quantities to have good estimates of these exponents. So, and moreover, it assumes stationarity. It assumes that you have some stationarity. It's only in this case that these exponents have a real meaning. And as I said, so since the embedded theorem is an existence theorem, it is really very difficult to estimate this exponent, and there is a bunch of methods to do so, and there is no consensus on what is the best way to estimate this exponent, and you find contradictory results and conclusions about, and even though if you assume that you can estimate them, this quantity is just a global quantity that gives global description about the system. And I think that it's because of this difficulty in measuring this, in estimating these global measurements, and in the weakness of the information that it gathers, that these methods didn't have, to the best of my knowledge, an impact in nonlinear speech processing.
Essentially, that just tells you the size of the subspace, right?
Yeah, it tells you. It measures. Yeah, and the divergence rate of nearby orbits. So it assesses a bit the complexity of the system without really saying more. So the question that you've been asking is that, well, not me, but physicists, is all this necessary to have these complicated things to deal with, and can we do more simple and still have more comprehension about our dynamical systems?
So when you say this is necessary, I mean, the Lyapunov exponent is a pretty simple measure. It doesn't really tell you anything.
Yeah.
Useful.
Yeah, really useful, and it's difficult to estimate.
Right.
Yeah, and it doesn't tell you that much. But a lot of work in nonlinear speech processing has been dealing with this kind of stuff. So it turns out actually that these kind of methods belong to what the physicists call the first phase of complex system theory. So where only global measurement can be assessed. So this starts with the Kolmogorov model of turbulence, the analysis of structure functions, the canonical representation of fractal or multifractal processes, the transient fluctuation analysis. So these methods, they recognize the existence of interacting multiscale motions, but there is no access to them. In simpler way, they recognize complexity of the system, but they don't tell you that much about the complexity of the system. Since the 90s, there is a new trend in the community of complex system theory, where it says, okay, we are going now to try to localize geometrically complexity. That means that where the complexity emerges and how it organizes itself. And there is a school which adopts the notion of predictability as a way to characterize complexity. And this is where the GeoStat team stands. Sorry. Oh. What's going on? What happens? Wait, it's moving.
By hitting space, you've got it to go. It just steps through as if it's a slideshow. If you get
Okay. So, in this school that adopt predictability as a way to characterize complexity, the basic principle is to say that for certain class of complex signals and systems, there is some thermodynamic observables that have a power law behavior. And even more is that what Antonio Turiel and Hussein Yahya have developed is that this power law behavior can exist at any point of the signal domain. So typically in mathematical wording is that given your signal S of x, there exists at least one multiscale functional, TR, that when you analyze it around the point x, you find a power law behavior in terms of scales. So D here is just the dimension of the signal S. So for speech, it will be just 1. And the important quantity here is this h of x. It's called the singularity exponents. And the hypothesis is that for this class of systems, there exists some geometrical superstructure that dominates completely the dynamic of the system. And that we can access to this geometrical structure by analyzing the level sets or some level sets, and they are characterized by the points where the singularity exponent is the same. So, in other words, you take your signal, you evaluate this multiscale functional, you try to find these h's at each point, and then you form the set of points that have the same exponents, the level sets, and some of them are actually the most important quantities that carry information. So in this way, this singularity exponent unlocks the relation between geometry and statistics, because basically what they say is that we are going to access to this structure geometrically, and these structures contain most of the statistical information. So it's kind of a way to bring together statistical signal processing and dynamical, nonlinear dynamical signal processing, which is the deterministic counterpart of statistical signal processing.
I think this is important, so I want to understand it.
Yeah.
There's a signal S of X or of time, and you're saying at some particular point in time, that signal has a property that can be expressed by this power law.
Yeah.
And I should care about that property because that property is measuring how predictable the signal is there. Is that why it's important?
Yeah, it's because, I mean, what is nice about the work of Antonio Turiel and his fellow colleagues is that they provide the way of precise estimation of this h at each point of the signal domain, and it gives also an interpretation of this exponent as a way to quantify local predictability.
But okay. Now, why shouldn't I just be like simple-minded and say, well, I'll do LPC, and I'll see what the error is right around here, and that's the predictability, or some other model that predicts a time series, and just apply the model and see what the predictability is.
You can do this, for example. Okay, you can take.
Or maybe
You can
that's how
take-
get the age, is that?
Excuse me.
Yeah, why not just do that? If I want predictability, why not just measure it?
No, but for instance, so it's what you are saying that you are defining your notion of predictability. So typically, what you're saying, I'm going to look at the residual, and where I have the highest peaks, they are the less predictable points. Okay, but here first, you are assuming a notion of predictability that can make sense or cannot make sense. The second thing is that you can do, for example, if you take just the highest peaks and do them as the source signal for your filter, it's not going to work that much because you have polarities in these peaks. So you can do. I mean, it's all about what do you mean about predictability?
Okay, so maybe you might get your estimate of H by doing something like LPC, even though that might be a bad or a crude approximation.
But if you do it, don't forget also that there is this notion of scale. So if you do LPC, you are just at the finest resolution of the signal, and you are going to have a definition of predictability at the finest resolution. Here, it tells you actually, I mean, I don't want to go into all the hypotheses. It tells you how the energy concentrate in the point X while it transfer across scales. So all this is based on from the notion of turbulence and energy cascades in turbulence.
Just make sure I'm still following. So H is the underlying dynamics of the system that you understand, that you can characterize. And the second term there is all the stuff that you can't characterize, all the noise.
The second stuff, this stuff is negligible. I mean, they say that for small scales, this term here, you can neglect it.
Okay. So I don't understand where the statistics are coming from. This is statistics of...
Yeah, I'm coming to this later. Because this is the first component, is definition of the singularity exponent.
So for each x, you can expand your original function into this form, right? For each x.
Yeah.
And but for each x, you have different alpha and different h. Is that true?
Yeah. You have different alpha, different h, but alpha actually it can cancel, and what governs the dynamics are this h here, because there is a way to show how. I mean, this alpha is also not that important. You can make it cancel.
So even if they are different, you can still cancel it.
Hmm?
Even if alpha is different for each different point, you still can.
Yeah, it's. I mean, in the estimation you can I mean, alpha is there, but in the you can get rid of it if in the estimation of h. And the important quantity according to this theory is this power law scaling, and not this constant this multiplicative factor.
Okay. And this only applies if R is going to close to.
Yeah, for small scales.
By the way, what's the meaning of R? Is R just the distance?
R just the
Is
scale.
R the distance?
It's the scale at which the resolution at which you are looking at the signal.
Scale of the signal. Okay.
So now I'm getting more confused. Because if there's multiple scales, and at each scale you've got your own h, then you've taken
No,
one.
it's
the
not.
H doesn't have an R subset.
No.
Well,
It doesn't depend on the scale.
H does not depend
That's
on
the
scale.
magic of the H.
Okay. H is a function.
Yeah.
Okay.
So typically from S, we are going to have access to this h of x and see what we can do with it for the moment. So, and the choice now of this multiscale functional is important, because if you choose it, for example, just as linear increments, you run into the well-known Holder exponents that are mainly used in fractal multifractal theory.
Okay, so R is the distance. R is the distance in the original signal space.
Well, that's one definition.
The one definition,
Okay.
but we don't adopt this definition, because actually these are just these quantities are only directional, and they are unstable, and they don't resist to noise, and they don't give you really interpretation about predictability. It's just about geometrical regularity of the signal. So these quantities are very known in the canonical framework of multifractal theory, but they are impractical and they are very difficult to estimate. But what Antonio Turiel and his colleague has proposed is to define these measure as the multiscale functional, which is called the gradient modulus measure, and which is defined from typical characterization of intermittence in turbulence, and it measures actually the local dissipation of energy, of kinetic energy. So you sum up, or you sum up all the variations of your signal in a ball around X. And then with this measure, you try to estimate the age.
With what is the gradient being taken with respect to? It's the gradient of your one-dimensional signal.
Here I mean, whatever dimension. Here,
Okay, so it's the gradient of your signal with respect to what?
It's to all your dimensions. So here it's just.
Oh, okay. So if in one dimension, the previous exponent you're talking about would be one approximation for the gradient. Or
it's difficult. If you write it down, it's not that. It's yeah.
This one here, that seems like an approximation for the modulus of the gradient as r goes to 0.
Well, you can see it as an approximation, but here you sum up all the variations in the ball.
Okay.
So you but if you want, you can consider it. But actually, just this measure here makes a lot of difference because they show that it describes better the variations around signal that looking just at directional increments.
Is that, if I got it, that's an integral over a surface?
Yeah.
And not over the volume, is that right?
Yeah.
Okay.
So by taking this multiscale functional, what these people say is that they can characterize the degree of local predictability at each point. How do they do this? That they say if we are correct in saying that there exists this geometrical structure that govern the dynamics, then from these geometrical structure, we can have access to all the information about the signal. So this is the original claim. And what they have done is that they show that for particular class of signal, this is true. So they take...
Wouldn't it be the bigger the value, the lower the predictability? Because if you're looking at the gradient, that's how fast things are changing. And if things are changing a lot all over the place, and you do that integral, you'd end up with a big number. And that would seem to mean that it's not predictable, because if you go over here, you're moving in this direction. If you go over here, you're going in this direction.
Yes.
Oh.
Yeah, but this is what it is. So to estimate, for example, an easy way is to look at the log-log ratio, and the things reverse. I don't know.
If you go back a slide.
Yeah.
This T.
That's another thing.
That's not the exponent.
This is not the exponent.
That's a
I see, okay.
that's not a statement of T, it's a statement of H.
Even if it's not the exponent HT, when this value is larger, HT will also be larger, right? Because it's just a log. Take a log is the HT.
No, it's the opposite. When it's large, the exponent is smaller. It's even if you
mean because R is less than 1. Okay.
yeah, it's very small.
Oh, yeah. Because I is less than 1.
So the claim is that if we look at a particular geometrical structure, we have access to most of the information. And here is, to answer your question, the relation with statistics is, they are going to show that this is indeed true for some class of signals. So you take these exponents, you assume that you can compute them, of course, and you look at the so-called most singular manifold. And the assumption is that the most singular manifold is the subset of points having the smallest singular exponent. So you compute your h's, and you take the smallest ones, and you form the subset of points that corresponds to the smallest exponents. This is called the MSM, the most singular manifold. And as I said, they claim that this MSM corresponds to the point where information concentrated at its transfer across scale, and that it governs the dynamic of the system. So, and they say if we are right, then we should be able to reconstruct. And actually, they developed a method for system reconstructability, which is here. So for natural images, which says that you can recover fully your signal by looking just at the gradient of the signal restricted. So this symbol means that it is a restriction over the MSM, and you diffuse it through an appropriate kernel. And this, in case of natural images, this kernel is universal and has this form which complies with the scaling property of the power spectrum of natural images. And there is a lot of applications and strong results in image processing using this formalism. So I recall you have now two components. This measure, the singularity exponent that we obtain from them, the MSM, the most singular manifold that allows us to reconstruct fully the signal from only the knowledge of properties of the signal on the MSM.
So what's the definition of fully construction? I would think you still have errors, right?
Yeah, there is in fact, in the real world, there is still errors, but you can never have perfect reconstruction, but they have what they show that they have very good reconstructions.
So you're saying that to the extent the model is correct, you have perfect reconstruction?
Yeah.
And then because the model isn't perfect, you don't have perfect reconstruction. Is that where the imperfection comes from?
It's got to be more, because there's this subset. It has to have to do with the size of the subset.
Yeah, because it's actually they have shown that this is true for in the continuous case, you have perfect reconstruction. For real world signals, as you said, it depends on how many information you gather here. And all the goal depends on what kind of signals. The cardinality of this set here can be low or big, and this gives you plus or minus about your reconstruction.
Say for continuous signal, you can completely reconstruct?
Yeah, because actually what they show you that this MSM is dense, in the continuous is dense in the signal domain, and you can recover everything from it. But this is the continuous case. So if we summarize now what we have is that there is this, well, I will say easy to compute quantity, which is the singularity exponent, even though it's not that easy. In the case of images, I mean, the way they compute it is a little bit involved, because it it uses a notion of local reconstruction to estimate the H's. So they evaluate local reconstruction around the point to give a value to H. So if you have good reconstruction, it means the H is big, and so it means that the point is predictable. Otherwise, when you have bad local reconstruction, the H is very low. And this is how you can pretend that this singular manifold corresponds actually to unpredictable manifold. So now this has been done in image processing, but if we look at this reconstruction formula, it looks a little bit appealing to what we know about speech. Is that imagine 1 second that we can do the same thing for speech signals. This will tell us that, oh, by looking at this H, we can probably have a really and easy access to the source signal. And if we can find the good kernel, then we are going to reconstruct. So it could be an alternative, a nonlinear alternative to our classical source filter model.
One of your objections earlier, which was that the source and the filter are coupled.
Yeah,
But they're not coupled here.
Yeah, they are not, or they are.
It seems like they're not. These are two different expressions.
Yeah, but when you look at this expression here, you are obtaining the source here after nonlinear operation of the full signal. So probably what you obtain, I don't know, because this will, it's not really decoupled. So, but anyway, we can still, if we can use this formalism this way and do the assumption that they are decoupled, why not? I mean, we. So let's now see what is going on in the case of speech signals. So I took exactly the same components, but I replaced now x by t. And let's use the same analogy as in 2D case and take the same multiscale functional. And we want to analyze this new formalism to analyze speech, but keeping in mind that we want to do, and this is very important because, as I said before, these nonlinear techniques that have been developed so far, they are very complicated, and people that get scared from them. And there is not that much, and probably that this is why they don't have that much impact in speech processing, besides the fact that, for example, as I showed before, we don't have access to a lot of information. So I want to try this formalism on speech signal but with the philosophy to do simple things that everybody understands, and also to develop efficient algorithms, to do things that people can easily implement. And the problem is that we don't have this nice reconstruction formula as in the 2D case. Okay, we cannot hope to have this universal kernel that reconstruct for speech signal. So
it's a problem of speech, not a problem of the.
Yeah. So, but still, just try to do something with these H's. So since we don't have the reconstruction formula, so we cannot use exactly the same way they estimate the H's, but we rely on a theoretical result that have been developed by Oriol-Pont, which say that if you assume that there is energy cascade behind your process, and then some other theoretical stuff, that the cascade variable is infinitely indivisible, then you can estimate your exponent just by summing up the so-called transition exponents, which in our case we compute just as the logarithm of the the ratio between the logarithm of the multiscale function and the logarithm of the scale, and you normalize.
I have to admit, I'm completely lost.
Okay.
Can you translate this into speech? I mean, what does H correspond to in a speech signal or a speech system? What information is in there?
So this is the point, actually, is that we are using, in the case of 2D, we can say fairly that these exponents correspond to local, they quantify predictability around the point, okay? Here we want to say the same thing. But at least personally, I feel that they don't have the right to say this, because we don't have the reconstruction formula that allows you to give this interpretation of local predictability. But I'm just going to call them singularity exponents, try to find a way how to estimate.
If I have a 2D image and I shrink it this way, I chop off some of the rows on the bottom, it's a little bit smaller, and I shrink it somewhere I don't have a 2D image. What if I shrink it down all the way to one row, then I have a 1D? Why does it all of a sudden break in that case?
What will break? I mean, if
So I think
it's this.
the difficulty comes from the intrinsic property of speech, not because of dimensionality. If it's from the dimensionality, then 1D is simpler than 2D.
Right.
Is there a class of signals that you
Like he
can
says,
find
from
in one
speech
dimension that you can
singular.
find a reconstruction formula?
Actually, they have done it but well. To a certain extent, for stock market series, so where it's the dynamics are not the same as in speech, of course, and but I think that for speech signal we have just to take. I'm very confident that we can that we can achieve the reconstruction formula, but just we have to take.
Is there a particular aspect of speech that makes it intrinsically more difficult?
Or if you take
Yeah,
a speech signal,
I
just
mean-
tile it across to the image.
There you
Right,
go.
or a spectrogram. A spectrogram is an image.
Right, a spectrogram is an image, so why is that?
No, but it's not an image coming from turbulence.
Of course it is.
And
It doesn't get much more turbulent than this.
Okay, I have a,
No, seriously, why?
Yeah.
I mean, why
No,
is it?
this formula doesn't work for. I mean, you cannot say that you can apply for any image and you will have this information about the physical process behind. No, it's not. It's not magical.
so if we took a picture of exhaust coming out the tailpipe on a cold day,
Of what?
the billowing smoke. Would that be, is that what you're talking about when you're talking about an image of turbulence?
Yeah, yeah. The smoke, like for example,
Yeah.
if you look cigarette and.
And so the theory tells you that there's some points in this image that you can take and then reconstruct.
Yeah.
But spectrogram doesn't
Statistically.
statistically reconstruct.
Right.
The spectrogram doesn't look like that.
Right.
And so that's why you're saying that speech is you can't directly apply this to
Yeah,
speech.
of course.
It's
and-
deterministic, not stochastic.
Wait a minute. I find it hard to believe that the turbulent image would be more compressible than
He's not doing it.
the non-turbulent. And turning the image into a few of these points, that's a lot like compression.
But it's a stochastic reconstruction, so it's going to have something that resembles smoke, but it won't be pixel for pixel accurate.
Is that
Yeah,
right?
Yeah, it's not going to be pixel for sure, but.
No, but I think it's more than that. I think he actually means it reconstructs it. It reconstructs something with the same statistical properties, but it actually reconstructs something that's like a mean square error close approximation.
I don't think so.
Well,
So actually, what do you mean by the word reconstruction? What is
For images.
For images is that you take the image, you compute your exponents, you find the lowest ones, and you apply the kernel here, and you have a good reconstruction of your image.
What does good mean?
Yeah, so good, it's...
No, seriously.
I mean, if you had a bunch of images of turbulence, would you be able to find, and you had the reconstruction, would you be able to find the source image? Would it look similar?
if you have...
So let's say I have 10 pictures of turbulence,
Mhm.
and I take one, and I try and reconstruct it.
Yeah.
And I see this reconstruction. Can I, as a human, pick out which of the 10 I used as a source for that reconstruction? Is it, I mean, do the images look the same?
Well, at least this is what they claim, that they are really looking at the same, is that you can recover, for turbulent images, you can recover all the
So
All the-
structure-
all the
structure
important
of the turbulence
fronts.
looks the same.
Yeah. Unfortunately, I don't have. I would, if I knew, I would have showed you examples of ocean dynamics.
You're not arguing for pixel by pixel mean squared error.
No, well, actually, for example, in if you are thinking about compression or, I mean, this physicist.
If we took a picture of Lena
Yeah, and actually, but
and we did this, and then we reconstructed it, would we say, oh, that's Lena? Or would we
yeah,
say,
yeah. Actually, this is true, but you know, they consider Lena as a natural image. You see,
So it's
And you
reconstructing
don't
the
need-
actual,
and
this-
the actual image.
So why don't spectrograms work then?
That's my question.
what?
It's, right, it seems.
Wait, a
that
natural
if
image
it's-
is not good, or because it's not turbulent?
It's so if I see that, I mean, you want that, take the spectrogram and reconstruct it. This is what you mean?
Yes.
I'm trying to figure out what you mean.
Yeah.
So if you do this and it can reconstruct Lena, why can't we do this and reconstruct the spectrogram?
First, and imagine if we can reconstruct the spectrograms, and then what?
Then you can go back to the time.
I mean, how are you going? You are going to pick some points, some MSM on the frequency domain, and
Well, spectrogram is isomorphic with a waveform.
excuse me?
From a spectrogram, you can reconstruct a waveform.
Yeah,
So
but
it's isomorphic. It has the same information.
So I guess,
Yeah, but,
right, so the point is, if we can reconstruct Lena, we can reconstruct the spectrogram. If we can reconstruct the spectrogram, we can reconstruct the waveform, and therefore it works for the 1D signal.
well, probably you're right. And you're giving a great idea. I will actually. I have thought at some point, but I thought that what would be the MSM when you look at the spectrogram, what would be intuitively the these MSM to what it will correspond to, or
I have no idea.
yeah.
That's what I'm trying to understand.
But
Yeah.
isn't phase important in images?
But there's enough overlap. Oh. Well, it's a 2D image, so yeah, there's a lot of, it's, I mean,
Image
a
is
spectrogram is
space.
constrained. Not every image is a valid spectrogram. Because it's a 1D signal.
Mm.
So it's a constrained image.
Yeah,
But
yeah.
probably I will do a test and send you the reconstruction and see what it. So where were? So anyway, in summary, we for the 1D case, we just adopted this way to estimate the exponents, which is very easy, very simple.
So I have a question, so I understand how this computation is happening. These individual h sub r sub I are calculated by the log ratio of this t operator,
Yeah,
which is your modulus gradient.
yeah,
So it's like how quickly is it changing at the scale Ri?
yeah.
And the denominator is the scale divided by what? What's its
Yeah,
FS?
wait, so it's the sampling frequency.
So that's a constant.
Yeah,
And then Ri is measured in time.
exactly. So it's your the scale of the interval you're looking at. So you see, it's very simple to compute.
It's trying to figure out what's happening across frequency. How quickly is the signal changing?
Yeah, because
Across
I prefer
scale.
scale. I prefer
Across
scale.
scale.
Yeah.
Okay.
So I said, now we have this way to compute H, and let's look how they look like. So this is speech signal from Timid, and the vertical red lines are just the manual transcription of phonemes in Timid. And if you look at the time-conditioned distribution of the H's, so here you have time, so you take 32 millisecond window, and you look at the histogram of the H's in each window. And you can see, well, here it's not very clear, but if you look closer, you see that actually the distribution of the H's is changing from phone to phone. But of course, it's not very clear from here. So we said, okay, so since the distribution is changing, let's just look at the simplest descriptive statistic. So we look at the local mean. And since we want to keep resolution the finest possible, we just look at the running mean of the H's. So we look at this function ACC as accumulation. And you can see that we have this nice behavior that it's almost piecewise linear functional with a breaking point at the boundaries of phonemes. And even you can see for shorter ones, see here, it describes the slope of this piecewise like linear functional, it's changing for adjacent phoneme. So you say, okay, let's do simple thing and fit a piecewise linear functional to this curve and identify the breaking points.
Wouldn't this be true even if you use very simple technique? You still can find this kind of behavior?
Yeah. Well, we've looked, and can you tell me of a simple technique that will do this?
Just for example, just the energy you can already got.
Yeah, if you look at the energy, you are not going to have this kind of piecewise linear functional with such a resolution.
So that 0 and 0 to t is you're running across the whole utterance.
Yeah. No,
Right?
but
that never gets reset, right?
yeah, but it doesn't mean here where you start, because
Right.
So the slope can be interpreted as a local mean of
Yeah.
the H.
Right.
But that's
So-
usually a flaw in the A to D, because usually a low pass, I mean a high pass filter at the front end. So the local mean should be 0. So it doesn't pass DC. I'm a little confused as to what this is getting at, because it's essentially it's essentially the lowest bin, the DC bin spectrogram. Oh no, I guess it's not, because it's over time, it's cumulative.
Right.
So it's the integral.
It's an integrated part.
Yeah, so it's
Slow pass.
It's a low pass filter. Perfect.
okay. So I'm interested to see how you look at this. So what are you saying?
Well, I mean, you're taking the speech signal and you're integrating over time, which is equivalent to, in the frequency domain, multiplying by 1/f.
Yeah, but here we are not taking the speech signal. It's not the speech.
What is that? Oh, that's your H.
Yeah.
Okay, I have no idea then. Sorry.
Yeah.
You're right.
Your
I
low
missed that.
pass filter here. H.
Yeah.
It's
It's
all that.
So go back a slide then. I'm sorry.
It's denoising that previous,
Yeah.
smoothing out the ripple.
Go back a slide.
Previous.
So you said that H would be low when you have maximum predictability. But
In-
around 0.3 looks like a fricative, which should be least predictability.
no, it's the opposite. When it's high, it's
Well, I don't read waveforms very well, but I think this looks like a fricative, which should be most unpredictable. I mean, this is definitely a vowel.
Well,
Yeah.
he has it labeled in the previous slide, what that is.
Oh, yeah,
It's
what's
the
it,
same
what's it
signal.
0.3?
Go back one slide.
Go, it's back or forward? No, back, other way.
Forward.
Yeah.
0.3.
It's an S.
Yes, that's affricative. That's maximum randomness.
Yeah. So
But it's got the lowest H.
it's yeah. This is what I say. It's
But
unpredictable.
now, can you just go back?
Okay, I thought small h was
The
predictable.
one before it.
No,
is
it's the
about-
opposite. Smallest h is unpredictable.
Towards negative infinity is unpredictable.
Okay.
Yeah.
That's what you're saying.
But
Oh,
hang
wait,
on,
that's-
if you go back one, the one before it's a vowel, and that's also low.
Yeah, there's not much difference between
Mm.
this vowel, which is very predictable, and this fricative, which is completely noise,
Compared to some of
random.
the other things that are going on.
Well, there seems to be some effect of scale, right? Because the most predictable thing is silence.
Silence is really predictable. Yeah, that part works.
But
Yeah, speech activity.
let me remind you is that I don't allow myself to talk about predictability at this point for these exponents. I talk about predictability for images, but still here you can see that it coincides a little bit what we are expecting. I don't know if you agree.
I'll go with that for now.
So wait, but the previous, the next, so you take the mean. Wait, is this the mean? Or is each point in this time window the mean vertically in the? Because
It's over H, so.
eight.
Yeah.
So you're integrating over tau h of right. All the but in the previous slide I thought your
That was
h of
H.
tau was a sum of other little h's.
Well, H in the previous one was a histogram
Of all
Yeah.
the h's that went up in a sum.
in a time,
Yeah, this is just the histogram.
Okay.
So
Our
I thought-
windows.
Go back one more. Yeah, so I thought h for any given time is a sum of.
Yeah, this is just a way how to compute. You can just.
Okay, so that.
So these h's are other transitionals here. You're just
Okay,
following.
So
the-
everything. So that's just h at a phone. Okay.
Forget this one. I'm just saying how we compute in this case, just to show that it is easy actually.
So one of the things you're asking is how would somebody in speech recognition look at a graph like this? It seems like the only really useful thing is like a spectral measure where you're trying to determine whether the sounds around it are similar or different. And in places where you have a linear progression of this integrator, you expect that the expected value of the h in that region is the same. So it seems like you can,
So yeah, I'm trying to eyeball.
if the sound isn't changing, then the h isn't changing.
Right.
And there's some
Yeah.
correlation there between the two.
But is there also like, is there any repeatability? So like there's an A at about 0.5, there's another A at about 2.5.
They're both sloped down.
There's yeah,
Well,
so
go back,
it's-
go back, I mean, I think this, I understand now, so go back a slide.
Is slope the informative thing? Because it's not absolute number. 'cause
So
they're
this
totally
previous thing is based on the fact, this next slide is based on the fact, this is constant, this is constant, this is constant. I don't know what's going on there, this is constant, and so they have a value, and when you integrate over time, that gives you a particular slope.
Yeah.
You're just interpolating between the two constant,
Yeah. I mean,
piecewise constant
Yeah.
things, right?
right, I think. So what happened to 0.4 on the next graph? Because here it's sloping a lot. So that's, well, it's changing, I guess. Huh?
Yeah, it's a,
Steep slope.
Yeah.
Yeah, I don't know what that means. I guess it's a, yeah.
Is there a significance for h is 0? So we've got in the previous slide we've got positive values of h and negative zeros
Yeah.
values of h. What's the significance of the positive
H
or
equals
negative?
0.
So according to theory, the negative ones are the most important ones. It's where you have low predictability, and the positive ones is the opposite.
Yeah.
So, and here we are looking at all of them. We are not at the MSM yet.
Yeah, but
It seems like context-dependent predictability, because like the two A phones are totally different.
absolute values. That's because of the integrator.
Yeah, because
Right,
if you look,
That-
So
that's-
I'm trying to
that's
think
causing
if it's,
context.
so what was the other one was
So,
like point.
Khalid, I want to draw everybody's attention to the clock.
yeah.
Yes. Oh, that's right. Whatever.
So-
3 o'clock
so-
to the reading.
Yeah.
Yeah, yeah. So, and here, so by this simple operation that you're saying, and so we compare to the state-of-the-art technique in phonetic segmentation. Well, don't look at the third row. This is just incremental improvement about this integrator, this ACC functional. So we compare to what we found is the best. So this paper of Dusan and Rabiner, which we compare on the full TIMIT database, so at least we can have fair comparison. And we have better results. But what is more important, we've been discussing this before, is that probably we should trust more, if this stuff makes sense, trust more the segmentation by this method than relying on the manual transcripts of TIMIT. So probably we should look at a typical example where normal, even manual transcription cannot find the regime, the transitions, and see if this method can find them. But unfortunately, we didn't do this because we wanted to go to look at other aspects. So to look at the MSM, this major component of the formalism. So here, a voiced speech, and here the H is now, just the signal H of T. And you see that from this picture here, you see that, and the red vertical line, they correspond to GCI locations extracted from EGG signals. So they are here also. And you see that the lowest exponents are around these GCIs. So this is directly by looking at the H. Here, a better example where we zoom. If we take now this, the MSM by 5% of the lowest exponents, you have this behavior. So here again, another voice signal. And you see that the MSM is located around GCI. The lowest exponents are all around GCI. And even another nice behavior is that the lowest exponent in these regions corresponds to the exact location of the GCI, according to the EGG signal. So it seems like this MSM corresponds to, has a physical meaning in speech, which apparently here is GCIs. So we said, okay, let's compare to what is going on in this field of GCI detection. So this basically, this level change functional, just you compare the mean of H's around the point, just to allow to have only one MSM point per glottal cycle. So it gives this red curve. And then we take the zero crosses of this this green curve, sorry, and we take the lowest MSM, the lowest exponent points, which is the closest to the peak. So just this is to guarantee that we are taking MSM point, the lowest one, and but the ones that are in one glottal cycle. So, and here are the performances. So there have been theses defended just last year by Thomas Drogman, and here are the results in clean speech. So you have two measures. I think Mark knows this stuff better than I do. Reliability measures and accuracy measures. So reliability measures are almost the same, but accuracy is always better. And according to Thomas Drogman, C-dreams and confirm or infirm, what you say, is the best algorithm and the most robust so far, according to his. So, and particularly when you look at shorter tolerance windows, we have better results. So we see again this, when we want to look at high resolution we have always this benefit because the method is sampling based. And I remind you that this is just by simple transformations of the H. So here are the results on noise, because in clean speech, most of the methods do well. So here you have accuracy, the hit rate, and here the last figure, you have the accuracy. So this is in the case of bubble noise, and you see that particularly for low SNR, we are.
This is adding noise to the EEG.
Yeah.
Speech signal.
To the speech signal.
But I thought that GCI was done. Oh, you have
uses
a parallel.
graduates.
You have a speech signal and a parallel EEG signal.
Yeah.
Yeah. And what is interesting is in the case of car noise, that the result seems to be very good. So it means that there is some robustness, and this has been actually showed in image processing and also theoretically that lowest H's are robust to noise. So well, I have to be quick. So this is, so we took this MSM and proposed it as a way to provide sparse linear prediction. So the idea is, so the L0 norm is the impractical ideal solution. Another, an approximation to this solution is the L1 norm, but it involves convex programming. So we propose just to downweight the mean square error minimization on the GCIs. And actually, Wednesday morning, there was a presentation by Pavu Alcu, who is doing exactly the same thing. Fortunately, I submitted the paper three months ago. So we did the same principle. He's using his way to compute GCI. So we downweight, and we have showed that we have better sparsity after we made a statistical test that by doing this method. But this is, I wouldn't say that here we are just playing about with our MSM stuff to obtain interesting results. So and then he was talking about formants, and so we have made the test that we, on a synthetic vowel, you have an exact estimate of the original transfer function, while the L2 norm is shifting formant a little bit. And also, so we have used this MSM to, you know that classical multiplace excitation coding operates in two stages, where in first stage you have to do, if you want couples, you have to do K searches of order n to extract pulse location, one after the other. And then you optimize all the pulses, or their amplitude jointly at the end. And this takes a lot of time, this first stage. So we replace this first stage directly by putting the MSM as the pulses. We say that the MSM gives us the location of the pulses. And then we keep the second stage of MPE the same. And here an example of what we find. So this is the original signal. This is the pulses given by the MSM. So their amplitude is computed using the second stage of MPE. And this is the reconstructed signal. And here we compare, so to the performances. So the best one is MPE, re-optimized MPE, because there is a first version in 82, which is relatively bad in SNR performances. Ours is here, and this one is one that was published last year using using compressed sensing methods. So we see that for low Ks, we have better results than these two here, but MPE is better. But MPE does intrinsically minimize SNR, so it's not surprising that he's doing a good job in SNR. But if you look at perceptual measures, we have almost the same quality, but we win a lot in computational complexity. So I want to make here just one simple conclusion. Actually, my interest is not in the performance or whatever percentages we gain. Is that I showed you a very simple nonlinear operation in the signal that allows to have easy access to some interesting local dynamics of the speech signals. So we saw that we can have access to GCIs, to phone transitions. Does this mean that this formalism is potentially good for nonlinear speech processing? I hope that the answer will come from you. So this is the perspective for the short time incremental research. Actually, Thomas Dergoman wants to use this for synthesis. In his system, he has a synthesis system. I heard that GOIs were very complicated to estimate, so probably we can take a look at them.
Maybe you have them. In the multiplayer pulse excitation, that second pulse looked very much like it might have been the GOI.
At the right
Really?
days.
Yeah.
You should.
So maybe you've solved it.
What does it mean, MSM for unvoiced speech? Normally, it should have a better meaning there because the assumption is that there is turbulence there. Is there just some random locations of unvoiced speech, or does it have physical meaning as we have found for voice speech? Are we looking at the right intensive variable? I mean, I have showed you this gradient modulus measure as our intensive variable. Is it the right? We have just copied from image processing. Is for speech, is this the right variable to look at? Can we have better estimates of singular exponents? Probably the idea is by reconstruction the spectrum. I will definitely. And I want to say a word that, so this is not in this talk, but Oriol Ponti is a physicist and mathematician guy who, in our group, is working on a way to infer directly the cascade energy, and this is through the notion of optimal wavelets. So he has already some results, but we are waiting for the final results where we can infer completely the cascade of the energy using a notion of optimal wavelets. So if we have this, of course, we will have another way that I will presented you today to look at these systems. But what would be very interesting is to have a reconstruction formula that is similar to the 2D case, and here it's open. Should we consider sound-dependent kernels? Because this would lead us then to what is interesting for you guys to have some new ways for feature extraction and so on. And also here you see that since we are little structure and we don't have a lot of manpower, it is very important to me to know what are the good problems to look at or what are the good applications to look at instead of just be tied by the lack of manpower. So I hope that you will tell me where this stuff, if it makes sense. If it's not, you can tell it to me and don't be nice to me. And what are the best problems to look at? And I think I'm right on time. Thank you.
If there's no further questions from the audience, there's a lot during the presentation.
Yeah.
I know a lot of us have to be somewhere at 3.
You have the meeting at 3, yeah.
But
Yeah.
One thing Khalid doesn't know, being a mathematician, is whether this work is interesting for speech or what kind of, he's looking for feedback on what kind of directions to take. Is that right?
Yeah, to have a figure from you practical guys who know better than me the area. And
one thing I would say is, I think you know, we are very interested in the dynamics, but I think it's the dynamics at a slightly larger scale. So it's at like the phone level or the, you know, the frame level rather than at the sample scale. You know, or like, you know, so what's the transition between words or syllables? Or I can imagine the dynamics of like conversational speech are not well modeled compared to.
So we're more interested in the dynamics of speech and articulators than we are of the air and the vocal tract.
Right.
So it's a higher level transitions that are of better interest.
Yeah, the dynamics, or like, yeah, the dynamics of the physical process. That's right. That's generating speech rather than the manifestation of that physical process, which is the little flow, airflow.
Well, I think in terms of segmental decoding and having some hints as to the segment boundaries could be very useful if those sorts of boundaries that you're identifying there hold up, you know, in a little bit of noise and in conversational speech. If it's generally true that this gives boundaries with reasonable accuracy, I think that's interesting.
Okay. So
Probably that your stuff requires looking at the host utterance, right, of the analysis.
No.
It's a local computation.
No, it's local computation.
Thank you.
Thank you very much.
Sorry,
Thank you for
sorry.
interacting.
You probably won't be here when the meeting's over.